So today's topic is about curve in three-dimensional space, or vector field in three-dimensional space, right? And let's recall what we learned in a domain in the XY plane. Okay. So okay, we have a domain, right? And you have a vector field on the domain P and Q. Okay. Now we know that F is conservative. Okay. Namely, it's those two are equivalent. Okay. It implies that Qx minus P, right, is going to be 0. Right. Now, conversely, it's not true, but we say this is also true if the domain D is simply connected. Okay. Okay. Yeah, it's not always sufficient necessary. Okay. Conservative, a vector field conservative. There are two different versions of definition, depends on which ones are equivalent. Okay, so F is conservative. The original definition, conservative. The original definition is the integral of this. Okay, is independent of C. Okay. So that means as long as they start from the same starting point, ending point was the same starting point and ending point. So the same end points. Okay, was the same end point. Okay. Conservative if that's a definition. Okay, and we can show that those two are equivalent to say F is greater than F. So those are the two facts. Yeah, in other words, those two are equivalent. That's that picture. All right. So now how do we check a vector field? Yeah, how to check whether this is our question we're going to study. Okay, how to check a vector field F. Okay, on a region in R3 is conservative. Okay, okay. So this is the region. Okay. So our pictures here. Okay, this is the region. A vector field is defined in three-dimensional space. Okay. So the vector field can be, I still use a D, huh? I don't want to use, domain. We simply call domain PQR because otherwise it's the same line. Confused again. There were 3 components. Now, first of all, you have to say what is the definition of the conservative. Okay, there are 2 versions. I said they're equivalent. The conservative means F line integral is independent of C with the same endpoint as long as they fix endpoints, and you have 2 different curve C from the same starting point and ending point. You don't get the different values. Okay, this is equivalent to say F is greater than F. Okay, why? How to do that? This F is constructed in the following way, and you fix an arbitrary point. Okay, you fix an arbitrary point, Okay, and then another arbitrary point you want to define, right? F is defined by the following integral, right? Where C is from a fixed point to that point. Now I don't need to specify C because it's independent of C. You can and you can verify the gradient for this F is going to be yeah, this vector field. All right. So in order to find the criteria to check, okay, one of these conditions satisfied, either independent, the integral is independent of C, or F can be returns gradient related to F. We have to find necessary condition. Okay, so we assume that capital vector is greater than F. Okay, so what does that mean? That means we have a P equals Fx, right? Q equals Fy, I equals Fz. Now, those are three components, P, Q, R, okay? All right, so let's check. As I told you, we can try Py, right? That was Fxy, and you can switch the order, and that is going to be Qx. That's the first equation, right? So Py equals Qx. That's a necessary condition. And then Pz equals Fxz, right? And that is Fzx. Now, what is Fz? Fz is the last term, or R. So Rx. So Pz equals Rx. Then I have to use a Q. I already have a Qx, Qz. Qz is Fyz. Then Fzy. Fzy is Ry. Okay, so I have a Qz equals Ry. So you have a three equations instead of one. Okay, over there you have a in dimension 2, you only have a one equation, right? Now you have a, but this equation is really similar to that equation, but we have addition to equations because in this involves Z. Now, how do we say one word those three equations are equivalent? So I'm going to introduce a notation called a curve. Okay, define, yeah, for a vector field. For a vector field, F, P, Q, R, and now I'm going to use a one simple notation instead of those three equations. I define a notation called the curve F, and I put together the first component. I'm using Ry, okay, using the last equation, Ry minus Qz. Now I have to in this order. I plus Pz minus Rx, J plus Qx minus Py, K. Okay, so this is still a vector in three-dimensional, okay? in three-dimensional space, still a vector. Okay, so the vector F, the curve of F is still a vector. Okay, the curve of F, if this is the vector F, okay, and the curve vector may be in that direction. Okay, so there's no direct, yeah, we don't know the angle in between those two vectors. All right, now what I did as the last step is, okay, yeah, this one, sometimes it's easy to forget which one should be first, right? This can be formally written as ijk, partial x, partial y, partial z, and pqr. Okay, now this is a formally, because I, j, k are vectors, not okay. Then you can compute the component of any. This is a vector, okay. So the component of any component of the vector, okay. And for example, the I part, right? The I part will be QR I, and J part will be, just delete the second column, the first row, P and R. And this is the last one will be P and Q, K, okay? And then you compute this determinant 2 by 2 matrix, okay? Then you get the above expression. Okay, so this is a fact, okay? And what we gather here is a theorem says that if f is gradient of this, then all those coefficients are 0. So then curl of f is going to be 0. Okay. The question is it a necessary condition? Is it a necessary condition? Okay, question. Yeah, question. And if the curl of a vector field is 0, okay, is f conservative, i.e. F equals greater than some f for some f, right? Just like what we did for the 2-dimension case. Okay, the 2-dimension, in other words, is okay. In other words, if f is the gradient of little f, then you have those 3 components of capital F satisfying this equation. So those are partial differential equations. If they're satisfied, can we express f as a gradient of some function? That's the question, right? But you look at that, look at the 2-dimension case. We have to assume these are simply connected. That means, that means that there's no hole in the domain. And same thing is true. So yes, the answer is, okay, if D, this is a domain. Yeah, I just say, just say F, okay. Let the F to be a vector field. Okay, we have to assume that it's differentiable sometimes, yeah. On a domain D, or in the domain, the 3-dimension in the domain D in R3, okay, and was whose component functions have a continuous partial derivative, okay. Okay. Now, we assume that D has no 3-dimensional holes, okay? In the sense, this is also called a simply connected, okay? Simply connected. It's good interior. In other words, this is there's nothing empty inside, okay? And this is not a simply connect. If there is a hole here, okay? This is not a simply connect. The reason is if you put the points here and have a loop, and this loop, you cannot shrink it to the point. Okay, imagine like a donut, right? The donut is not simply connected. Okay, any loops inside, you cannot pull to that point. Okay, and the ball is a simply connected. And any point inside any loops, they can shrink with inside the ball to the point. This is a simply connected. Okay, so those are the examples. Then the curl of f equals 0 and implies F is greater than F. Okay. Now, in the book, they make it easier. They don't want to explain what is simply connected mean. So in the book, they just assume that F is defined whole R3 in the whole space of the whole space. Of course, it's simply connected. Right. This is a topological concept in mathematics. So we solve the problem. We answer the question. We have to find it, right? We have to do some problems. Okay. Right. The logic is very clear. If F is a gradient of some function, then all those components is going to be 0. Okay. So simple partial and the 3 partial differential equations here. And conversely, we want that is also true. Okay. And after we check, the components, and we can, if they all, if the difference of the partial derivatives is all equal to 0, then it must be conservative. And in other words, you have a function. So let's take a look at the example. Okay, this example, let's look at FZ. Okay, so this is a y square z cube, 2xy z cube, 3xy square z square. All right. Okay, so this is a 3-dimensional. Yeah, it's a 3-dimensional vector field. Let's compute the curve. Okay, I forgot which one PQ. It's very hard to memorize this detailed formula, honestly. Okay, the curve, which one first? R, Q, P, R, Q, P. That's difficult. Okay, nobody easily can find out, to memorize all those orders with the subunits. Okay, I do have my friend. He can memorize all the phone numbers in the yellow book. Can you believe that? That's so he he got a PhD degree in mathematics, and he found out he has super memory. So mathematics, you don't need a super memory. Okay, you understand material. So he got another PhD in history. Okay, world history. So he can tell you anything almost. All right, so those are special. So let's look at the gradient ijk. Okay, this is a formula. It's easy. I don't know, but here, yeah, we can easily memorize this formula. Okay, all right, let's compute it. I'm going to put the details here. This is z. Okay, no, yz. Okay, yz, because I want to get I. Okay, expand the yz. Okay, so you will get 2xyz cube, 3xy square z square, I minus y square z square, 3xy square z square, and j and k. All right, so let's check one by one. This is a partial derivative with respect to, cross product, right? With respect to y, so 6xy z square minus, and the partial derivative of this function with respect to z is a 6xy z square. Well, that is going to be 0, right? And here's a partial derivative, and this will be minus 3y square z square, okay? And this will be 2yz cube minus 2y z cube. Okay, so they're all equal to 0. Great. Okay, so that's a guarantee because the function defines the whole R3. Okay, so this vector field is defined on the whole R3. Of course, it's simply connected. Okay, no hole set. Right. So we are able to find this function. Now, what are you going to find is a function. We are going to do is fx, yeah, write down this unknown function. Fy is going to be 2xy z cubed, and fz is going to be 3xy squared z squared. All right, so step by step, all right. Step by step, I'm going to define the f. So you integrate both sides with respect to x, okay? So this side you will get f x, y, z. Now you fix y, z, right? So this will be just x, y squared, z cubed, and plus a function, and this depends on y, z, okay? Then you differentiate, then you plug them into the second equation and the third equation. So fy, which is going to be 2xyz cubed plus gy, right? Then fz will be 3xy squared z squared plus gz. But we know this is going to 2xyz cubed, and we know that this 3xy squared z squared. So clearly the partial derivative of g is going to be 0. Okay, with respect to y and with respect to z. So that implies g is going to be constant. Okay, it's nothing to do with that. So we find the function. Okay, so that means the general formula for the f is xy squared z cubed plus a constant. Okay, right. So our f is gradient of this. Then, yeah. So you just integrate both sides and then you find it. Let's do one more problem. Okay. Before we do that, let's look at a special case. Okay. You know, in two-dimensional if the vector field in two-dimensional plane D, but you can view it as a three-dimensional. Okay. So this is a vector field. Let's call it F. Yeah, I'm going to call it F1. Okay. So you have P, X, Y, Q, X, Y. It's a two-dimensional, right? But you can embed in a two-dimensional plane into three-dimensional space. So you can get a three-dimensional vector field. Okay, so the first two components is a P, Q, and the third component is 0. So you get, yeah, so you get this, right? And this can be defined on the whole cylinder domain, cylindrical domain. Yeah, this is if this domain is D1 and that domain D1 is D times negative infinity, positive infinity. Okay. All right. So let's look at what does a curve mean. Curve of this vector in three-dimensional space is nothing but yeah, actually it's nothing but 0i plus 0j and plus qx minus py k. So this is a term, only term left. You can do computation quickly. So this is a term in two-dimensional case, right? So curl of f equals 0 if only f qx minus py is 0, right? So our theorem right now today is the general case. Okay. Right. So this is going to be 0 because this equation is necessary condition for the f being a gradient of some function, okay, in dimension. All right. So that's the two-dimensional explanation for the curve of a vector field. So this is a vector, you know, vector field. In K is a constant vector. All right. So let's look at another example. Okay, let's consider f x y z to be 1 sine z y cosine z. So we want to know whether this is conservative or not. Okay. Again, we have to use IJK. Unless you already memorize all the 3 components. Okay. 1 sine z, y cosine z. Otherwise, we have to repeat this again. Okay. So here's okay. So let's look at this, right? And then partial z 1 y cosine z, and that is the last one. Will be okay. So let's take a look at it. The first one will be cosine z minus cosine z. I think it's gonna be 0. Second one is 0 minus 0 j. The third one, that's a 0 minus 0. Okay. So clearly it's gonna be 0. So the curl of the vector field is gonna be 0. So it's defined on the whole R3. So I believe that there should be f should be gradient of some function. Okay, so I have to find out. Okay, so that is going to be sine z, fz is going to be y cosine z. Okay, all right. So repeat the same procedure. It's guaranteed we can find such f, right? So integral of this. So I get fxy z. It's going to be a constant, so it's x plus g of yz. Okay. Then you plug it into the second function. I will get when differentiate with respect to y, I get dy equals sine z and gz. Okay, because when I differentiate derivative of the x with respect to y, z are 0, right? It's going to be y cosine z. Okay, so we have to continue. It's not like a constant. All right. Yeah. We have to plug into the second equation, the third equation, and you got this too. So integrate gy dy. Okay, I got g y z, and then it's going to be y sine z plus constant. This constant I use h z. Okay, then I plug into the second equation. So gz equals y cosine z plus hz. And this should be y equal to cosine z, right? So that means hz is okay, it's 0. So that means h is going to be constant. Okay. All right, so we determine the j, and we also get f. So my final answer is going to be x plus y sine z and plus constant k. Okay, so that is a function we are looking for. Yeah, this is a j. Okay. Not all of them, are conservative. Sometimes you're given vector field, you're not able to find the little f so that the vector field is greater than greater because take arbitrary vector field like this. Here's x, right? Y, right? Y squared plus x squared, and then and the z squared x, for example, right? So this is vector field. Okay. Now let's look at this curve. Okay. So this I, J, K. Okay, I'm going to compute it. So I get I, right? So yeah, let's repeat this. This is going to be partial x, partial z, xy. Yeah, how do I get this? You delete, if it's j, you delete this column, this row, and this column. So what is left is become that matrix. Okay, okay, plus. Right, so let's compute this. So when you differentiate that term, it's going to be 0, right? When differentiate that, is also be 0. I. This will be z squared minus 0, j. And that'll be 2x minus x. Okay, okay. 2x. Hold on, this is the x. Yeah, y squared and x squared, right? 2x, x. So the answer will be negative squared j plus xk. So it's not going to be 0. Okay, so that means there's no f x y z such that f is greater than this function. So not majority vector field is not conservative. Okay. Why? Because if it is, then the curl of f must be 0. Okay. Now for a vector field, okay, there's another important function, another notion here. For a vector field in 3-dimensional space or 2-dimensional space, it doesn't matter. Okay, 2-dimensional space, a vector field can view a vector field in 3-dimensional space. Okay, for a vector field R3. Okay, so F is going to be PQR. Okay, then the divergence, the so-called divergence of F, which is defined this, is going to be partial derivative of P with respect to X. Okay, so add them together. Now this is easy to memorize. Just the X for the first term you differentiate with respect to X. For the second term you differentiate with respect to Y, and the third one you differentiate with respect to Z. Okay. So this is a function, not a vector field. Okay. As an exercise, we should we have the following theorem. Okay, if well, that's true for in general. if the vector field coming from the curl of some vector field H, okay, for some H, let's use it. We can use any, right? We can say PQR, for example, okay? Then the divergence of F must be 0. Wow. So that actually answers the question if where the vector field can be expressed as the curl of another vector field, right? And it's easy to verify directly, okay? The reason is, and remember, I just write down the curl of this vector field. The curl of this vector field have a 3 component, right? Remember, there are 3 components. It's R, Y, Q, Z, I plus PZ, RX, J plus QX, PYK, right? So when we compute the divergence of a curl of H, you just needed to differentiate the first column with respect to X. So RYX minus QZX, okay? Plus, that's a PZY, we differentiate with respect to Y, and then you differentiate the last one with respect to Z. Okay, now you have all those 3 components, total 6 components. But you will see that those 2 will be canceled out. And this 2 will be canceled out. And this 2 will be canceled out. Okay, so they all canceled out. It's going to be 0. Okay. And so now let's look at another. So what happens? The vector field is going to be the gradient of F. Okay. Then the divergence of F. Okay. It is going to be because this is going to be Fx, Fy, Fz, right? So when you differentiate, you get Fxx, Fyy, F Z and Z. All right, and this is denoted by Laplace of N. Okay. All right, so the divergence of vector field, if vector field is gradient of some function, then the divergence is going to be 0. Yeah, now find this thing. Given vector field, right? You have 2 possibilities. One is can be written as a gradient of some function. Another is can be viewed as a curve of some function, right? So the necessary condition, if f is can be written in that, is going to be the necessary condition. Right, the necessary condition is going to be the curl of f should be 0 for this one, and for this one, right? The divergence of f is going to be 0. Did you know? You check that, right? So there's a possibility if the divergence of f is 0, maybe you can find you can express f as a curl. Okay, but we don't know the anything. But this the one on the left side is true, right? As long as the domain is simply connected. Okay, that's what we did. The right hand side, we don't know, but that this divergence of is necessary if f is curl of some vector field. But it's not easy to find h. Okay, it's not easy to find h. Okay, here's a remark. If divergence equals 0, it is not easy to find the h such that f is going to be curl of h. Okay, maybe it's impossible. We don't have a such theorem here. Right, we don't have a such theorem here. Right, so let's take a look at some examples. Okay, right, we compute, let f x y z to be sine y z I and sine z x j and sine x y k. Okay, so let's compute the curl and the divergence. Okay, okay. So let's compute the curl. Okay. The curl is going to be ijk because I forgot the formula again. I only memorized this one. Get the formula. It's in some logic. Okay, sine yz, sine zx, and sine xy. Let me quickly check whether this is going to be 0. I don't think so. Okay, so so I can write down the formula. Okay, I just want steps. Let me write down what we got. Remember, I can do the computation quickly. So this will be cosine xy, partial derivative with respect to y. So again, x here minus this is vx, the partial derivative, cosine zx. Okay, this is I. Okay, then I look at these two terms, y cosine xy minus y cosine yz. Okay, and the last term will be z cosine zx minus z cosine yz. Okay, and this, so no one of them is 0. Clear, it's not going to be 0. It's not going to be 0. Okay, so this is not going to be the gradient of some function. So let's take a look at divergence f. So divergence of f is just a derivative of each term. Okay, each component, right? You find out they are equal to 0. Each of them is 0, so that's 0. All right, my question is f equal to curl of some h for some h? And then you have to solve how many equations? It's not easy to get this. Okay, I'm not sure you were able to find such h. Okay. Because the divergence of f is 0 is a necessary condition for the f being the curl of some vector field. Okay, so if you let h to be p, q, r, you have to find the 3 functions using 3 variables. That's difficult part. Okay, so if we do one, and I'm going to write down the 3 questions, right? The 3 questions is a p ry minus qz should be the first component. Okay, and then pz minus rx is the second component. Maybe by guessing, trying, we can get this. Okay, the last component. Now how do we get PQR, right? Okay. You cannot simply express it. All right. Yeah, it's not easy, right? So we can try, right? But I don't know how to do it. Okay. So not every partial differential equation is, you can solve. All right. Right. Yeah, let me find another problem. Okay, let's take a look at the following one. The first component 0, second component, okay, the third component y to the fourth c cubed. Okay. I hope you can, yeah, I hope we can find out the curl of f and the divergence of f. Okay, can you try this? Yeah, give a minute to look at, okay? Okay, let's do the computer. I think the divergence is easy to compute, okay? Divergence, as long as you memorize formula, that's easy to memorize. That's the partial derivative of first component 0, then you differentiate the second component, and that is x cubed z squared. then differentiate the last component with respect to z, and the y to the fourth z square. Okay, so this is not going to be 0. It's not going to be 0. So if it's not 0, definitely f is going to be the curl of some vector field for any h. Okay, for any h. All right. So now let's look at the curl of the vector field. Okay, the curl of the vector field is going to be ijk and have a 0, x cubed yz square. Okay. Okay, the first one will be this part, right? So when I differentiate, I get a 4y cubed z cubed minus 2x cubed y z. Okay, I just computed, okay, cross plot, right? And okay, then minus, okay, minus those two, right? The last column and the first column. So that'll be 0, that's 0, j. Plus, okay, plus, I think it's just 3x squared yz squared. Okay, okay, so you got 3 components. It's not going to be 0, neither. Okay, so that means f is not going to be the gradient for any f. Okay, yeah, that's bad, right? But I think if you already know the curl of f, if f can be written as a gradient of a letter f, then the curl of f must be 0. Okay, those are the two are almost equivalent. Okay, those are two almost equivalent. Okay, so now let's take a look at next problem. I think I did most of the problems now. Okay. Any other problems in the book? Yeah, 14. Oh, we did it. Let's do the last one. 18. Okay. So f is going to be e to the x sine yz. Okay. And z e to the x cosine yz. And y z to the x cosine yz. Okay, all the terms is yz then cosine sine, right? Right. So we are going to check the curl of this vector field. Okay. I think the gradient definitely is not going to be 0. Okay. So just take a look at the curl. So this ijk e to the x sine yz, z e to the x cosine yz, and the y e to the x cosine yz. Okay, the first term is those two columns, right? If these two columns when I differentiate, wow, it's lots of terms here. So the first term will be, I'm not going to write exceptions. The first term is by the product rule. Okay, that's the first term. Then differential with respect to y, right? It's negative. Yz e to the x sine yz. Okay. I minus in those two terms. Okay, when I differentiate, I get y e to the x cosine yz. Then I differentiate with respect to z. So I get y e to the x cosine yz. Not too bad. Plus, okay, plus those two, right? So when I differentiate, you get this minus y minus z e to the x cosine y z. Okay, so carefully we check. This term is 0, right? This term is also 0. Why the first term is not 0? Almost 0, right? Let's double check. So I wish, yeah, the first term, yeah, differential with respect to y, differential with respect to y, and minus, oh, I forgot the other term, minus the other one. So e to the x cosine yz, and minus, that's plus, differential with respect to z. So zy e to the x cosine yz. Okay, so they're all equal to 0. Great, this very complicated function, they're all equal to 0. So that means f is possible for some function. Okay, okay, this is possible. Okay, because the curve is 0. Okay, so we have to find it. Okay. So we're going to find this. All right. So the first step is integrate the first equation with respect to x. So I get f here. Then that's the integral with respect to x. It's still the same function. But don't forget you have function depends on yz. Okay. Okay. Then you have to plug into the second equation, the third equation. Okay. When I apply the second equation, fy equals when the differential with respect to y, I got z in front of that. Okay, let me rewrite it again. So I got z e to the x cosine yz plus gy. Okay. And this will be y e to the x cosine yz plus gz. Okay. Now this should be e to the x cosine yz. This should be y e to the x cosine yz. Let's compare both sides. Ooh, good. So that means gy should be equal to 0. Gz also should be equal to 0. So that means g is going to be constant. It's k. Okay. So we got function. Our function fyz is going to be e to the x sine yz. Okay. Sine yz. Okay. And plus any constant. That's fine. So that f is going to be the gradient. Okay. The divergence of this function is not going to be 0. Okay, the divergence. I don't think so. Yeah, the divergence of this function is not going to be 0. So f is not going to be the curl of any h, vector field h. Okay. Okay. Now, for the if f is divergence, right? And then here what do we have to do? Okay. So if f is gradient of some function on some connected domain. Okay. Then if I give you the path C, here's P and Q. Then this F dr along the C is just equal to FQ minus FP. It's independent of the path, only depends on value function of the two endpoint. The reason is you can parameterize, okay, T is greater than A less than B. So this is going to be the integral from A to B, F, right? And F prime T dt. But this little f, well, this capital F is little f, the gradient of little f. Okay, by the channel, this is nothing but the derivative of f. Okay, so therefore, it is going to be, okay, and that is FQ minus FP. So it's independent, the passes from P to Q. There's another one here, doesn't matter. Even there's a hole here, doesn't matter, okay? Yeah, it's not necessarily connected. Okay, so it depends on, it depends. So if we ask you to evaluate the integral, you maybe double check whether it's a conservative or not. Okay, otherwise the path you're given is very complicated, and you probably don't need it to do that, right? Okay, so here's a simple problem, right? We did the computation before. I just use this same function, okay? Use this same function, okay? So evaluate this line integral, and here is going to be f dr, where f is going to be e to the x sine y z I, z e to the x cosine y z j, plus y e to the x cosine y z k, okay? And the C is a triangle with from 0, 0, 0 to, 0, 1, 3, then to the point 2, 1, -1, then to the back to the point. So there'll be 3 points. I have to stay from where to where. So starting point is here. Another point is 1 and 3 here, right? It's A, B, and the 2. I'm going to change it to a positive. It's going to the top. Okay. So somewhere here, C. Okay. So it goes like that in the space. Okay. But if you really want to evaluate this line integral along the 3 lines, it's very complicated. You have to parameterize all the curves. However, if you notice that, curl of f is 0. And then f is gradient of some function. Okay, and you find the f, it's easy to find out. We just find it from above, right? E to the sine yz. Okay, but for this particular problem, we don't need it because it's closed curve. So therefore the integral of this is going to be 0, because since C is a closed curve. Okay, if it's not a closed curve, then you just you have to find the f. Okay, so if I just say if C is a curve You have a starting point, ending point, right? And for example, x equals, x equals t, y equals t squared plus 2, z equals t cubed plus t plus 1. I just make it one more complicated. Okay. Then how to evaluate the integral. Then the integral of this is going to be the value of the two endpoints. Okay, so in that case, the starting point is going to be when t equals 0, 0, 2, 1. And the end point is going to be when t is 1. It's 1, 3, 1, 1. It's also 3, right? So it'll be f 1, 3, 3 minus f 0, 2, and 1. Now, what is our f? We already find the f, right? Yeah, we find the f. So let me write down the f, right? F is e to the x sine yz. So actually, f is going to be e to the x sine yz. Okay, so f is e to the x sine yz. E to the x is 1, sine yz is 9, and the e to the x sine yz 2 times 1 is 3. So it's going to be e sine 9 minus sine 2. That's a pretty strange number. But that is, yeah, that is what we got here. Okay. Anyone has a question? So I did not pay attention. Okay. Okay. So I stopped recording here. That's